Welcome to the Distributed SQL Summit session on physical data modeling with Yugabyte. My name is Brian Whitmore. I'm a principal pre-sales engineer, and I'll be guiding you through some of the basics and advanced topics in data modeling and optimization for Yugabyte. This includes the process, some general rules of thumb, and then we'll dig into Yugabyte specifics, optimizations that allow you to take full advantage of Yugabyte's capabilities, and some examples. The process begins with your existing data model and your application use patterns. You want to consider which data you're going to be selecting most frequently, which data you're going to be writing or updating, and what those use patterns are going to look like. Is your application 70% write? Are there some tables that you update very frequently? Or is your application going to write or update data infrequently, but read it 5 or 10 times for every time that it's written? Those types of considerations will drive how you choose to optimize portions of your data model, either as read optimized or write optimized. And you'll need to consider the specific objectives of your application. In order to do this, in order to execute on this, you'll need to review your primary keys, you review your indexes, look at some query plans, see how the operations are making use of your data model, and then potentially refactor or denormalize some tables. So some background and a reminder that Yugabyte is a distributed database. And that means that your data is going to be spread out onto multiple servers. That's going to give you the ability to scale easily, but it also means that if I have to visit every server to complete a query, that I'm giving up a lot of that scalability. In order to facilitate distributing your data, every table has a primary key. So that doesn't necessarily mean that it is unique, but it at least tells Yugabyte for each row in the table, there's one and only one place in the cluster that can be the primary copy of that row at any given point in time. So that's how Yugabyte knows where to go when it needs to read that row and where to start when it needs to update or write that row. That also means that ORM data models with keys that are not used by joins are not particularly helpful in choosing the position of your data. So that's a consideration to keep in mind if you're migrating from that type of data model. Now, indexes will follow the same rules as primary keys in that an index will be broken into parts and spread across multiple nodes in the cluster, again, to facilitate scaling. But that's still going to work for you because for any given index lookup, that key is going to tell you which node to visit to begin that process. So in order to optimize in a distributed environment, there's really 3 rules of thumb. The first one, it really sounds like a cardinal rule of databases, minimize the amount of I/O that it takes to do an operation. That's true for all databases. And in the case of a distributed database, you really focus more on minimizing network I/O than anything else. Network round trips take time. And when you're trying to optimize response time, minimizing the number of round trips is going to be the best way to keep things fast. If you have to visit more than one place in the network, you want to try and do that in parallel. The other thing that you want to look at is you want to maximize utilization of all of the nodes that are in your cluster. So you don't want to get into a situation where 90% of the workload in your app falls on one node and the rest of the cluster is sitting idle. So in order to fully utilize the hardware, you want to make sure that you're selecting keys that are going to give you a good distribution. Now, It might seem like this is a trade-off or a compromise, and in most cases, it's not. It means that you want to pick a good column for the distribution that puts all of the rows used by a query together in one place and puts all the rows used by another query, a similar query, but on a different row, puts all those rows together in one place, but a different place. So just keep your use cases in mind. That's the third rule. And as we go through some of the examples, we'll touch on a few different use cases so you can see how to optimize for those. So our tools to implement the rules are, first of all, primary keys. That's the critical choice because it determines where a row lives. Secondary indexes, because that gives me another chance to pick the node where some data will live. If I have too many of them, it can make writes expensive, but they can be very useful. So that's part of my design consideration of whether I'm heavily read or heavily write optimized, or a sweet spot in between where both are fast. Obviously, I want to try to keep the number of total tables at a manageable size so that my data model is easy to conceptualize, fewer things to optimize, and fewer potential surprises of somebody using it in a way I didn't anticipate. And then finally, the last tool in the toolbox is denormalization. And when we get to that section, we'll get into some details about when and where to use it. So for primary key selection, I'm going to repeat this a bunch of times. This is what determines where a row lands in the cluster. So there's two components to the primary key. There's a part of it that I highlight with parentheses. That's the partition, the part that actually chooses where the row lands. And then the rest of the columns in the primary key, that's going to determine within a tablet which rows are written near each other. I'll also bring up sequence numbers. A lot of times sequence numbers are used liberally in classical applications, and you do need to really carefully consider whether a sequence number is the best way to solve a problem in a distributed system. As you might imagine, having all the nodes agree on sequencing would require network crossings. There's things you can do with caching blocks of sequence numbers to make that more efficient. But if all you really need is uniqueness and you're modernizing an application for a distributed environment because you've decided that the scalability, the high availability, the other advantages of distributed SQL are what you want, then consider if a UUID meets your uniqueness requirements, and try to eliminate sequences where possible. So let's take an example of an inventory table as our first example. And the primary key, you can see that the store ID is in parentheses, meaning that we're going to group together all of the inventory records for a store on the same place in the cluster. So there'll be one node in the cluster that's going to be doing all of the work for a given store ID. And on that node, you'll find all of the products in that store. And then presumably, since you have more than one store, the other stores will be spread around the cluster in a similar arrangement. Now, if you have a low number of stores, this is potentially a hotspot. But if you have 3,000 stores, then this is a good choice and lends well to scalability. Another way that I might organize the data in the same inventory table is instead to break it up based on product ID. In that case, I'd be saying that all of the information I have about a given product is going to be together in one place. And when I get there, I'll find the rows for each of the stores that have that product. I probably have a lot of products in my catalog, so this might also be a reasonable way to distribute my data without getting hotspots. The main thing that you're considering here is which data do you want to live close together? And this is going to be driven by your access patterns. So very often you're thinking of either how do I load my data? How's it arriving? And am I going to be able to distribute that data to all the nodes in the cluster as it's arriving so that writes will scale? But also, when I read my data, ideally, each read should go to one and only one node if I can help it. And again, I'm going to try and optimize my data model to achieve that. So I might find that I've made a choice for how to distribute the data on the table, but it doesn't cover all of the reads with that optimization that I'm looking for. I might need to add some additional indexes. So in this example where I've used the store ID to determine where a row is going to land, I might find that I need to build some indexes around product ID that can help me land on one and only one node for queries that are product driven. And if I get down to that last example, that's what we call a covering index. You'll see that I've included additional columns as part of the index. And in fact, I've got an in-store count. So the actual count of my inventory table is part of the index there. So this is the type of index that you would build for a query that says for a given product where I have more than 5 of them in stock, give me the stores that satisfy that condition. And also I can look at some of the data and metadata associated with those inventory entries just from an index scan. So from a network efficiency point of view, it's one RPC to go to the correct node that has all of the records that satisfy that query. And because it's about a single product, so I only need to go to one node to do that. Once I get there, I immediately satisfy the inventory count portion of my query and retrieve any data and metadata necessary to satisfy that. So I can do that all in one RPC round trip. So Yugabyte indexes are very powerful. Especially with that ability to have a covering index as a secondary index and get another opportunity to optimize where the data is going to live within my distributed cluster. So for example, the base table is split up on the basis of store ID, but the index is split up on the basis of product ID. And I'm repeating the last slide, but I really want to drive the point home that you can have both. Now, it does mean that when I update a given row, that isn't a single node operation. That is going to have to go to 2 different nodes because that's the way the data is going to be laid out when I've used a different column for the secondary index. But I think that for many applications, you'll be able to find those cases where it's worth spending a little bit extra on the updates to make sure that the reads, especially if they're very numerous or they need to be very fast, to make sure that the reads are well optimized. So getting that trade-off right, it's going to not only improve your response times, but it means that you'll be able to run with less CPU, less memory for a given number of transactions per second. And that's ultimately going to make your deployment more economical. So to summarize indexes, pay attention to your primary keys for data placement. Make them compound, especially if they are compound in the original data model. If you've already got a good candidate from your previous data model, you may as well use it. Take advantage of covering indexes where they can help your reads complete in a single network crossing, and avoid sequences if you can. Consider if a UUID satisfies the requirement for uniqueness, and try to avoid having a hotspot around sequence generation, and structure your applications to use UUIDs instead. So from there, let's talk about denormalization. So the obvious reasons to denormalize is it helps you minimize the number of tablets that you have to touch by reducing the number of tables that you have to touch during an operation. Another advantage is that data that's used together gets stored together. So again, very common optimization in databases, but especially important if you're trying to eliminate network crossings. And it can help you align the way the data is stored better aligned with the way the application uses the data. So the more you know about the use case and the way the application will actually be implemented, the better you can determine whether or not denormalizing is appropriate. I'll comment that you've seen with covering indexes and just primary keys in general, how it's possible to have two tables that when they are frequently being joined, if they're sharded by the same column or columns, then the shards that join, at least on an equality join, are going to land on the same node, and that also eliminates a network crossing. It's just that if you have 3, 4, 5 joins in a query, it gets more and more difficult to maintain that type of an optimization across lots of tables. And so you may need to consider eliminating some of those joins with denormalization. So obvious reasons not to denormalize. Maybe you've profiled the workload and you found that that operation that joins 4 or 5 tables, you don't do it very frequently, or it's already fast enough to meet your requirements. Or maybe you have one thing that you're joining pretty frequently, but it's well optimized and there's no reason to denormalize. Stick with what you got. Maybe you don't want to duplicate data. In some cases, the data duplication can be avoided. On YCQL, you have access to static objects that can avoid a lot of repetition. But on YSQL, it's regular SQL. So if it's a different row, it's a different data item. So you don't have access to that. And if your application cares very passionately about whether or not those multiple copies of the data are always synchronized, then you might have to update multiple rows under a transaction rather than individually. If that's not a burden that you want to carry, maybe you don't necessarily want to denormalize a part of your data model. And then there's the debate about, well, if I start doing a little bit of denormalization, it clutters up my data model. It makes it harder to figure out when I need to join and what I should be joining because there's these extra columns. I think that's a very individual thing that database purists are probably going to feel more natural in a fully normalized world. But a lot of application programmers, especially ones that come from a business background and probably best understand the business logic may not feel that way. They might be a lot more comfortable with having a wide table that gives them all the items they need when they need to go to read it or update it. And they may be more comfortable with a data model that doesn't require them to do as many joins. So, part of this is just a consideration of whether or not your data model will be used correctly and what is the best way to build it defensively. So once we have decided on that, we can figure out what are some of the approaches to denormalization. And so there's the obvious one, but let me show you a couple of not obvious ones first. So most denormalization techniques expect that there's a clear hierarchical child and parent relationship. The N by M cyclical relationships, those are harder to denormalize, but let's start with an example where I've got 0, 1, or 2 children for each parent, but it isn't an arbitrarily large number. It has a bound. If that's the case, then I can consider just listing those objects in a row, and I have them all together now in one row. So it's a sort of an unusual form of denormalization, but where applicable, this allows you to eliminate a table, eliminate a join, and satisfies the condition of being able to get all of the data that I need close together, close to where I use it. Most of the time, my fan-out relationships do not necessarily have an upper bound on the number of children, but if they do, this is a case where I might be able to do that. The more common example, I'm potentially going to be able to use an enum to eliminate a reference table. So, for example, if something comes in sizes small, medium, large, XL, etc., there's a finite number of those. I might occasionally have to add a new entry, but for the most part, that's a pretty fixed population. While I'm on this table as an example, I'll talk about another way that I can eliminate a child object from my database and not need to have a whole separate child table. If I have 2 columns, a parent ID column and a child ID column, then I can make a rule internally where I agree with my application developers that if you see a parent ID and the child ID is null, then that's a row in the parent table. And my data and metadata columns will describe a parent. If I see a parent ID and a child ID both populated, then that's telling me that the child has a relationship to the parent. And if I see a parent ID null and a child ID populated, then that's just a child entry, not associated with any parent. And again, the data and metadata are going to be just describing the child object. So that's a way, again, to eliminate a table and eliminate a join, but it's got some logic overloaded into whether or not certain columns are populated. Now, when you're building indexes, that's an opportunity for you to use a where clause in the create index statement, where you can say is null or is not null for some of those columns, and get indexes that make it a little easier for somebody to use the table correctly, as well as make it efficient. But that's a somewhat advanced example, and you might want to consider carefully whether or not that's maintainable in your environment. So to summarize, just like any other database, It really is all about minimizing I/O to make things go fast and run in the smallest resource footprint. And minimizing I/O for a single query and minimizing response time, that usually means not crossing the network more than once if you can help it. But that's a trade-off. I might need to write to 2 or 3 places so that most of my reads can go to one place, or I might need to shift that depending on what my application looks like. If it's write heavy, then I wouldn't do that. I want to optimize placement, especially if I've got tables that join frequently. The rows that join together should live together. And index choices give me a second chance to optimize when the primary key didn't cover all of my needed use cases. And indexes can speed up writes too by getting you to the right place to start them. And where necessary, or where it will give you a big uplift in performance or a big savings in resource footprint, denormalize so that you have fewer tables to manage and fewer joins in the course of your most frequent and lowest latency operations. Thank you very much. It has been a pleasure presenting.